Thank you. This is a brief, so the equation, and we got the characteristic equation from last time. The general topic for today is going to be oscillations, which are extremely important in the applications and in everyday life. But the oscillations, we know, are associated with the complex roots. So they correspond to complex roots of that characteristic equation, r squared plus br plus k equals 0. I'd like to begin, most of the lecture will be about discussing the relations between these numbers, these constants, and the various properties that the solutions, oscillatory solutions have. But before that, I'd like to begin by clearing up a couple of questions almost everybody has at some point or other when they study the case of complex roots. Complex roots are the case which produce oscillations in the solutions. That's the relation, and that's why I'm talking about this for the first few minutes. Now, so you get what is the problem? The complex roots, of course, there will be two roots, and they're complex conjugates of each other, so they'll be of the form a plus or minus bi. Last time I showed you I took the root r equals a plus bi, which leads to the solution. The corresponding solution is a complex solution, which is e to the a t a plus ibt. And what we did was, the problem was to get real solutions out of that. We needed two real solutions. And the way I got them was by separating this into its real part and its imaginary part. And I proved a little theorem for you that said both of those give solutions. So the real part was e to the at times cosine bt, and the imaginary part was e to the at sine bt. And those were the two solutions. So here was y1, and the point was those out of the complex solutions, we got real solutions. We have to have real solutions because we live in the real world. The equation is real. Its coefficients are real. They represent real quantities. That's the way the solutions, therefore, have to be. So the point is, these are now real solutions. These two guys, y1 and y2. Now, the first question almost everybody has, and I was pleased to see that at the end of the lecture, a few people came up and asked me, yeah, well, you took a plus bi, but there was another root, a minus bi. You didn't use that one. That would give two more solutions, right? Of course, they didn't say that. They were too smart. They just said, what about that other root? Well, what about it? The reason I don't have to talk about the other root is because although it does give two solutions, it doesn't give two new ones. Maybe I could indicate that most clearly here, even though you won't be able to take notes, by just using colored chalk. Suppose instead of a plus bi, I'd used a minus bi. What would have changed? Well, this would now become minus here. Would this change? No, because e to the minus ibt is the cosine of minus b, but that's the same as the cosine of b. How about here? This would have become the sine of minus bt, but that's simply the negative of the sine of bt. So the only change would have been to put a minus sign there. Now, I don't care if I get y2 or negative y2, because what am I going to do with it? When I get it, I'm going to write y, the general solution, as c1 y1 plus c2 y2. So if I get negative y2, that just changes that arbitrary constant from c2 to minus c2, which is just as arbitrary a constant. So in other words, there's no reason to use the other root because it doesn't give anything new. Now, there the story could stop, and I would like it to stop, frankly, but I don't dare because there's a second question. And I'm visiting recitations, not this semester, but in previous semesters in 1803. So many recitations do this, I have to partly inoculate you against it, and partly tell you that some of the engineering courses do it, and therefore you probably should learn it also. So there's another way of proceeding, which is what you might have thought. Hey, look, we got two complex roots. That gives us two solutions, which are different. They're not, neither one is a constant multiple of the other. Why not? So the other approach is use as the general solution y equals, now I'm going to put a capital C here. You'll see why in just a second, times e to the a plus bi times t. And then I'll use the other solution. C2 times e to the a minus bit. These are two independent solutions, and therefore can't I get the general solution in that form? Now, in a sense you can. The whole problem is the following, of course, that I'm only interested in real solutions. This is a complex function. This is another complex function. It's got an I in it, in other words, when I write it out as u plus iv. If I expect to be able to get a real solution out of that, that means I have to allow these coefficients to be complex numbers and not real numbers. So in other words, what I'm saying is that an expression like this, where the a plus bi and a minus bi are the roots of that, are complex roots of that characteristic equation, is formally a very general complex solution to the equation. And therefore, the problem becomes, how from this expression do I get the real solutions? So the problem is, I accept these as the complex solutions. My problem is to find among all these guys where C1 and C2 are allowed to be complex. The problem is which of the green solutions are real. Now there are many ways of getting the answer. There's a super hack way. The super hack way is to say, well, this one is C1 plus ID1. This is C2 plus ID2, and I'll write all this out in terms of what it is, you know, cosine plus sine, cosine plus I sine, and don't forget the e to the at. And I'll write it all out, and it'll take an entire board. And then I'll just see what the condition is. I'll write its real part and its an imaginary part, and then I'll say the imaginary part has got to be 0, and then I'll see what it's like. That works fine. It just takes too much space. And also, it doesn't teach you a few things that I think you should know. So I'm going to give another. So let's say we can answer this two ways by hack. In other words, multiply everything out. Multiply all out. Make the imaginary part equal 0. Now, here's a better way, in my opinion. What I'm trying to do is, this is some complex function, u plus iv. How do I know when a complex function is real? I want this to be real. Well, the hack method corresponds to saying v must be equal to 0. It's real if v is 0. So expand it out and see when v is 0. There's a slightly more subtle method, which is to change I to minus I. And what? And see if it stays the same. And see if it stays the same. Because if I change I to minus I, and it turns out the expression doesn't change, then it must have been real. See that? V must have been 0 if this expression doesn't change when I change I to minus I. Well, sure, but, well, you'll see it work. All right, now that's what I'm going to apply to this. If I want this to be real, I rephrase the question for the green equation, the green solution, as change. So I'm going to change I to minus I in the green thing, and that's going to give me what conditions, and that will give conditions on the C's. Well, let's do it. In fact, it's easier done than talked about. Let's take the green solution and change. So I don't want to, well, I better recopy it. C1. So these are complex numbers. That's why I wrote them as capital letters, because little letters you tend to interpret as real numbers. So C1, e to the a plus bit, I'll recopy it quickly, plus C2, e to the a minus bit. Okay, we're going to change I to negative I. Now, here's a complex number. What happens to it when you change I to negative I? You change it into its class? What do we change it into? Its complex conjugate, right? And the notation for complex conjugate is you put a bar over it. So in other words, when I do that, the C1 changes to C1 bar, complex conjugate, the complex conjugate of C1. What happens to this guy? This guy changes to this guy changes to e to the a minus bit. This changes to the complex conjugate of C2, now times e to the a plus bit. Well, I want these two to be the same. I want the two expressions the same. Why do I want them the same? Because if there's no change, that will mean that it's real. Now, when is that going to happen? That happens if, well, here is that, if C2 should be equal to C1 bar. That's only one condition. There's another condition. C2 bar should equal C1. So I get two conditions, but there's really only one condition there, because if this is true, that's true too. I simply put bars over both things, and two bars cancel each other out. If you take the complex conjugate and do it again, you get back where you started with. Change I to minus I, and then I to minus I again. Well, never mind. Anyway, these are the same. This equation doesn't say anything that the first one didn't say already. So this one is redundant. And our conclusion is, that the real solution to the equation are, in their entirety, I now don't need both C2 and C1. One of them will do. And since I'm going to write it out as a complex number, I'll write it out in terms of its coefficient. So it's C1, let's just simply write it. C plus I times D. That's the coefficient. That's what I called C1 before. And that's times e to the a plus bit. There's no reason why I put bi here and id there, in case you're wondering. Sheer caprice. And what's the other term? Now the other term is completely determined. Its coefficients must be c minus id times e to the a minus bit. In other words, this thing is perfectly general. Any complex number times that first root you used, exponentiated. And the second term can be described as the complex conjugate of the first. The coefficient is the complex conjugate, and this part is the complex conjugate of that. Now, it's in this form, many engineers write the solution this way, and physicists too. So scientists and engineers will include. Write the solution this way. Write the real solutions this way in that complex form. Well, why do they do something so perverse? You'll have to ask them. But in fact, when we study Fourier series, we'll probably have to do that at one point. If you work a lot with complex numbers, it turns out to be, in some ways, a more convenient representation than the one I've given you in terms of sines and cosines. Well, from this, how would I get, suppose I insisted, well, if someone gave it to me in that form, I don't see how I would convert it back into sines and cosines. And I'd like to show you how to do that efficiently too, because, again, it's one of the fundamental techniques that I think you should know, and I didn't get a chance to say it when we studied complex numbers that first lecture. It's in the notes, but that doesn't prove anything since I don't think I made you use it in an example. So the problem is now, by way of finishing this up, to change this to the old form. I mean the form involving sines and cosines. Now again, there are two ways of doing it. The hack way is you write it all out. Well, the e to the at, a to the a plus bit turns into e to the at times sine, cosine this plus I sine that. And the other term does too. And then you got stuff out front, and the whole thing stretches over two boards, but you group all the terms together, you finally get it. By the way, when you do it, you'll find that the imaginary part disappears completely. It has to, because that's the way we chose the coefficients. So there's the hack method. Write it all out. Blah, 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 blah. And nicer and teach you something you're supposed to know. Write it this way. First of all, you notice that both terms have an e to the at factor. Let's get rid of that right away. I'm pulling it out front because that's automatically real and therefore isn't going to affect the rest of the answer at all. So let's pull out that. And what's left? Well, what's left, you see, involves just the two parameters, c and d. So I'm going to have a c term, and I'm going to have a d term. What multiplies the arbitrary constant c? Answer. After I've removed e to the at, what multiplies it is e to the bit plus e to the bit. Let's write it ibt. And the other term is plus e to the negative ibt. You see how I got that? Pulled it out. And how about the d? What goes with d? D goes with, well, first of all, there's an I in front that I better not forget. And then the rest of it is I, so it's ID times. It's e to the bit, e to the ibt, minus now e to the minus ibt. So that's the way the solution looks. It doesn't look a lot better, but now you must use the magic formulas, which I want you to know as well as you know Euler's formula. Even better than you know Euler's formula, okay? And they're a consequence of Euler's formula. They're Euler's formula read backwards. Euler's formula says you got a complex exponential, here is how to write it in terms of sines and cosines. The backwards thing says you got a sine or a cosine, here's the way to write it in terms of complex exponentials. And remember, the way to do it is cosine A is equal to e to the IAT IA plus e to the negative IA divided by 2. And sine of A is almost the same thing except you use a minus sign. And what everybody forgets, you have to divide by I. So this is the backward version of Euler's formula. They're the two of them taken together are equivalent to Euler's formula. If I took cosine A, multiplied this through by I, and added them up, on the right-hand side, I'd get exactly e to the IA. I'd get Euler's formula, in other words. All right, so what does this come out to be, finally? This is this particular sum of exponentials you should always recognize as real. You know it's real because when I change I to minus I, the two terms switch, and therefore it's real. The expression doesn't change. What is it? This part is twice the cosine of BT. What's this part? This part is 2I times the sine of BT. And so what does the whole thing come out to be? It is e to the AT times 2C cosine BT plus I times, did I lose possibly a, no, it's okay. Minus, I times I is minus, so minus 2D times the sine of BT. Shall I write that out? So in other words, it's e to the AT times 2C cosine BT minus 2D times the sine of BT, which is, since 2C and negative 2D are just arbitrary constants, just as arbitrary the constants as C and D themselves are, this is our old form of writing the solution, real solution. So here's the way using sines and cosines, and there's the way that uses complex numbers and complex functions throughout. Notice, they both have two arbitrary constants in them, C and D. Two arbitrary constants that you expect, but that has two arbitrary constants in it too, just the real and imaginary parts of that complex coefficient, C plus ID. Well, that took half the period, and it was a long, I don't consider it a digression because learning those ways of dealing with complex numbers and complex functions is a fairly important goal of this course, actually. But let's get back now to studying what the oscillations actually look like.